Okay, hello everyone. So we are now in week 10. Assignment 3 is now released, right? So I will be going through your tutorials and your lab for week 10, which covers the lecture material from week 9, right? And it's going to be used for your assignment question, right? So all 3 of the videos, which is the first one on HuffmanCoding, the second one on Elias coding, and your last and final ones, which is your LAMPERSIF. We will look at LAMPERSIF77 and LAMPERSIF SS. So it will be 3 separate videos. HuffmanCoding is going to use in LAMPERSIF. Elias coding is also going to be used in LAMPERSIF, right? So in other words, all 3 videos is going to be required for your assignment. Okay, so your lab questions are very straightforward, and you notice I never really want to discuss your lab questions because they are nothing except programming question. Okay, so the most important thing is I will explain using your tutorial questions, right? What is the concept of the algorithms, and I will explain it from an implementation point of view. So afterwards, when I go through your HuffmanCoding, I will explain how are you supposed to implement it for it to be efficient, and it is the implementation which I will expect for your assignment. Okay, so your lectures material are here. If you pay attention in Arun's class, you should be able to understand most of it because it is quite simple. Okay, so question 1, question 2, question 3 is going to be about Huffman, right? And I'm going to explain Huffman using a whiteboard now. Okay, so in a normal machine, if I have a character, let's say A, I will need to save it in the form of 1 byte, right? 1 byte or 8 bit. Why? Because if you were to look at your ASCII, right, your ASCII is from 0 all the way up to 256. Okay, so if you were to calculate 2 to the power of k equals to 256, k equals to what, right? So k should be 8. If I open Google and just put 2 to the power of 8, right, you're going to realize it's 256. Okay, so yeah, if I were to save hello world, okay, I will have 1, 2, 3, 4, 5, 6. Remember the space is also another character. 7, 8, 9, 10, 11. Right, so I will need 11 bytes for me to save my string, okay, or 88 bits, right, because every single character is 8. But you may actually ask yourself, for example, alphabet A, right? The alphabet A, the ASCII number is actually 97, right? So what is 97 in binary? 97 for decimal, right? So I open Google, decimal to binary, right? Then if I were to just type it out, right, 97, okay, it's actually 11000001. And if you were to count the number of bits, 1, 2, 3, 4, 5, 6, 7, right? So if I want to save A, right, I only require 7 bits. But why am I risking 1 additional bit, right, just to ensure everything is conforming, right? And the reason is quite simple. If you were to look at the string of AA, right, if I were to represent it in such a form, 11000001, 11000001, right, and when I tell you it is AA, you understand it's 97, right? So let me cut off here, 97 and 97, right? Sounds reasonable. But how am I supposed to know I'm only using 7 bits and not 8 bit, right? Because I can also slice it in such a way. Okay, so if I were to slice it in such a way, right, 11000011, right, convert everything here, which is my 8 bits, is going to be 195. Okay, and my balance here is going to be 10001, right, which is 7 king. So if you were to look at your ASCII cable, right, 195 is actually another character, 7 king is also another character, right? So yes, I'm able to encode AA into bits, right? And because I know A is 97, I can only use 7 bits. I can save a lot of space, right? Because I'm saving 1 bit per character. So if I have Q A, I'm saving 2 bits. If I have a very long paragraph, I'm actually saving a lot of bits, right? So if I might your dollar sign is 36 and so on, right? So the number of bits which you require is actually less. Okay, so when I encode, I can save bits. The problem is when I decode, I have no idea how am I supposed to slice it, right? Is it only 2 character? If it's 2 character, is it 97, or is it 1957 king, right? What if I realize it is not only 2 characters, but it's 3 characters, right? So if it is 3 characters, right? If it's 3 characters, can it be the following? Or can it be the following? Or can it be the following, right? Or if I have 4 characters, 5 characters, 6 characters, right? I'm not able to decode anymore, right? But if I were to set everything to perfectly 8 bits, right? So if I were to set everything to perfectly 8 bit, right? So AA is going to be 0, 1, 1, 2, 3, 4, 5, 6, 7, right? Okay, 0, 1, 1, 0, 0, 0, 0, 1, right? So I will automatically know the first 8 bit, right? The first 8 bit, right? Here will be 97, here will be 97, which is A and A. So even if I have additional bits, it's totally fine, right? 0, 0, right? If I have a lot of bits. Okay, I will just slice 1, 2, 3, 4, 5, 6, 7, 8. First character, 1, 2, 3, 4, 5, 6, 7, 8. Second character, and so on, right? Which is why our characters are always saved in the form of 8 bits. Okay, this is why your characters are saved in 8 bits. Yes, I'm using more memory, right? But as a trade-off, I'm able to encode and decode without any problem, without any issue. Okay, but I'm wasting a lot of memory. That's all. So if you consider I'm trying to compress, right? I'm going to encode, or I'm going to compress English language, right? So you realize your English words are all A to Z only, right? Assuming it's all lowercase, right? Then I will have a few ASCII like space, right? I will have space, I will have new line, I will have period, comma, colon, right? That's it. So over here I got 26 characters, 1, 2, 3, 4, 5. Here I got 5 characters. In total I only have 31 characters, right? If I want to have 31 characters, I realize I can fit 31 characters into 2 to the power of 5, right? Okay. So in other words, I only require 5 bits. Why am I wasting memory with 8 bits, right? Each character I'm wasting 3 bits, right? So you're going to come across a lot of dilemma, okay? And this is where HuffmanCoding actually comes in, right? The power of HuffmanCoding is when you make a tree, right? When you build a tree, right? The tree which you're building is a binary search tree, right? So if I were to build a tree here, 0 1 0 0 1 0 1 0 1, right? And let's say I put a few alphabets. Let's say it will be A, B, C, D, E. Okay, and let's say if I were to give you a lot of bits, 1 1 0, right? I'm just randomly putting bits. I don't even care what it is. Okay, so what is going to happen is, right, I'm going to traverse my bits one by one along my binary search tree, right? If it's 1, I go right. If it's 0, I go left. Okay, so the first one is 1, means I go right. The second one is 0, means I go left. Third one is 0, means I go left. Right, then I reach a leaf. This is a leaf, right? So because it reached a leaf, right? So I know my first 3 bits is actually alphabet G, right? So let me slash out. Here will be G. Then I repeat the process again. 1 0 0. I reach another leaf, right? So here is going to be G. I move on. 1 1. I've reached a leaf, so it will be C, right? Oops. Right, so it will be C. Then I begin here 0 0, reach a leaf, right? So it will be A. Then 1 0 0, it will be C, right? This is the concept of what we call prefix free, right? Where no character is the encoding of one character is not the prefix of another character, right? So if you see A will be 0 0, B will be 0 1, C will be 1 0 0, E will be 1 0 1, and C will be 1 1, right? You realize no one, right? There are no one character, no one encoding is a prefix of another one, right? It's what we call prefix free. Okay, so if you were to go back to your tutorial question number 3, right? Does Huffman encoding always hear a prefix free code word for the characters is encoding? If yes, why? If no, why not? Right? The answer is yes. Why? Because what I'm constructing is a tree and my characters are all in the leaf, right? So if I have a character here, let's say X, right? So let's say if I put a character here, X, my X is not a leaf. X will be 1 0. You realize 1 0 is a prefix of D and E. It is no longer prefix free. Okay, but since all my characters are in the leaf, it is guaranteed to be prefix free. Okay, it is guaranteed to be prefix free. So in your assignment, right, when you want to decode a character, right, if you want to decode a character, you will definitely need to build a tree. If you were to search online, a lot of the online implementation actually do a hash table, right? So it will be the key, it will be the value, right? The key is going to be my encoding. 0 0 will be A, 0 1 will be B, 1 0 0 will be D, 1 0 1 will be E, then 1 1 is going to be C, right? Here is what you're going to see online. And the problem with the online one is, as I go through my bits one by one, right? 1, I need to search in my hash table. In other words, I need to hash 1 and see if it exists in my hash table. If it doesn't exist, I need to concatenate another bit and search again 1 0. Is 1 0 in my hash table? It's not inside. Concatenate again and search, right, if it's inside, right? So you realize you always have to hash multiple times, right? Hash multiple times, and each time you hash, you need to search over and over and over. So if you were to look at the online implementation with a hash table or dictionary, it's wrong. I see it in your assignment, I minus your marks, right? because this is a repeated question, and based on of the past year marking scheme, right, the marks which I minus here is 1 mark out of Q1 at the very minimum, right? So it is actually a very big penalty. So when you want to decode, right, you will always build a tree and traverse through your tree one by one. And make sure when you traverse through your tree, only use a pointer and move your pointer across your entire bit string. Please do not slice, right? If you slice and slice and slice, I will slice and slice your marks until you get 0 marks, right? Remember, slicing is very inefficient. All you need to do is just to use a pointer and traverse. 1, right, 0, 0, right, finish, move my pointer, we start back from the root again, 1, 0, 0, right? So your pointer just move, it doesn't slice. If you slice it, I'm going to slice your marks. Okay, so here is how you're supposed to decode your HuffmanCoding. Okay, so why I've covered the decode first, in my opinion, if I cover the decode first, it will help you understand better why we are actually doing it. Okay, so you can actually see, because eventually when you want to encode, if you look at your assignment question number 2, right, your encoding will have the header. You will use your header, right, when you decode to build a tree, right? So I'm explaining the decoding side of things, so when you encode, right, you know what you're required to perform. Okay, so this is the first one. Okay, so we will now move to your tutorial, right, question 1 and question 2, right? So read up on your own, right? So I'm going to go through it one by one now. Oops. Okay, so I'm going to combine question 1 and question number 2, where I'm going to try to encode A, B, C, D, E, right, in terms of their probability 0.4, 0.2, 0.2, 0.1, 0.1. Okay, so the concept is very simple. I want to build a tree based on the smallest probability, right? So currently, what I'm seeing here is 5 characters, right? The higher the probability for it to occur, I want it to be shorter, right? So if I were to name it, right, this is my character, this is the probability or frequency, right? The more frequent it is, let's say I have 100 characters, right? So my probability of frequency is going to be 40, 20, 20, 10, 10. Okay, this is a frequency. So if I need to encode A 40 times, I want my A to be as short as possible, preferably either 0 or 1, right? So if A occurs 40 times, if my string is A, and everything is 40 times, I can encode it with 0, 0, 0, 40 times, right? Or 1, 1, 1, 40 times. So I can encode 40 A's using 40 bits. Okay, now imagine if I encode A with a bit of 1, 0, right? So if I got 40, A will be 1, 0, 1, 0, 1, 0, 1, 0, right? 1, 0. Everything here is going to be 40 times, but each one is 2 bits, so I require 80 bits, right? You realize you actually waste a lot of bits. Okay, because when we compress, we want it to be as space efficient as possible. Okay, so we want the highest probability or highest frequency to be as short as possible. We want the lower probability, the less occurring one, to be as long as possible, right? Then if you see here, if you look at the tree, you should notice a pattern. The deeper I go into the tree, right? If I go deeper, it will be longer, right? So if you see A have a height of 2, right? 2 bits. B have a height of 2 bits. If you look at D and E, height of 3, okay, we have 3 bits, right? So there's actually a relationship between the number of bits and height. So when you build a tree for your Huffman encoding, you want the highest frequency one to be at the top, the minimum height, and you want the lowest frequency to be at the bottom, the maximum height. Okay, so this is the concept behind it. So note frequency and probability is pretty much the same, right? The frequency of A over total character, right? Over total character, right, equals to 0.4, right? So you realize the algorithm doesn't change because of the character will be divided by the same one anyways. Okay, so how are we supposed to do it? Okay, what I want is I want to look for the two smallest numbers in my list. 0.4, 0.2, 0.2, 0.1, 0.1, right? So 0.1 and 0.1 is the two smallest one. So when I build a tree, right, I want my D 0.1 and E 0.1 to be at the leaf, right? Remember, every character is the leaf. It will be 0, it will be 1. Okay, so when I combine both, it's going to be DE. So what is going to change here is going to be DE 0.2, right? Because 0.1 plus 0.1, I'm going to have a combine of 0.2. Okay, then once again, I want to look for the two negative. So each time I say look for negative, you realize it is actually very efficient. I need to perform a ON search, right, to search for the two minimum numbers or the two smallest number, right? So it is actually very inefficient, and afterwards I'm going to tell you how to make it efficient, right? So here for 0.2, I actually have two options, right? The first one will be B and C. The second one will be C and DE. Okay, so let's see what happens if I go B and C. If I go B and C, it's the same. B will be 0.2, C will be 0.2. If I combine both, right, it will be BC, which is 0.4. Okay, BC, which is 0.4. Now, if you were to observe here, right, you realize the height of my tree maintained at 1 for both, right? Imagine if I were to combine, let's say, here, C and DE. If I were to merge C and DE, right, what I'm going to get is here will be C 0.2, and if I were to combine both, it will be CDE 0.1. You're going to realize the height of my tree actually become 2. Okay, so by right, if the numbers are the same, I should prioritize the one with the shorter number of characters, right? So here my length will be 1, length will be 1, here my length will be 2. So if I were to go back to your tutorial, this is what it meant by your second question, right? Always merge two of the shortest height, right? Two of the shortest height, right? But your problem here is how do you calculate the height, right? Because what it means is here will be B and here will be C, right? Here have a height of 1, here a height of 0, here also have a height of 0. Does that mean I need another variable to keep track of the height? For example, DE have a height of 1, right? Do I need to maintain a variable? The answer is no, right? Because you know height equals to log, because it is a binary search tree, log of n, right? Or the number of characters, number of character, right? So which is why we can just use the length, right? Length of B is 1, length of C is 1, length of E is 2. So it will be 1, 1, 2. So if I were to merge and all have the same 0.2, I will choose the 2 smallest one here, right? So you will make use of the length, right? There's no need to calculate the height. I know in your tutorial it actually mentioned the height, right? But as what I've discussed here, I mean, it's something which you should know. Height equals to log n, right? So that's all, right? Okay, and then you will merge accordingly. I won't finish the question here. Why I won't finish the question? Because now I'm going to show you how to implement it efficiently. Okay, I'm now going to show you how to implement it efficiently. Okay, so I'm going to begin as what your question begins. Okay, A, B, C, D, E. I'm going to have the probability, right? I'm going to have the probability of frequency. Okay, and I'm going to have what I'm going to do here, right, is I'm going to put all of it into a heap. So when I put into a heap, remember, you do not want to insert one by one element into the heap because that is very, very noob, right? You want to perform an operation which we call EP5. So we have learned EP5 in 2004. We have proven EP5 to be O of n, right? And we also have a recap on binomial heap, Fibonacci heap, right? EP5 will be amortized into O of n complexity as well, right? So please do not insert one by one. If I see you insert one by one, means your complexity becomes n log n instead of O of n. And what happens if your complexity is I minus max, right? So you want to EP5 it, right? So how do you perform your EP5? Right, it depends on which min heap you use. If you use your array min heap from 1008, right, you want to put everything into your array and you want to sync from the n over 2 nodes onwards, right? Refer back to your 2004. Your 2004 lecture notes by Kenya Anderson, right? You actually cover it. Okay, or if you use a binomial heap or a Fibonacci heap, I glad for you because that's what you should be doing, right? It's not a sarcastic clap, right? In fact, if I were to be the one who set this question, right, your assignment 4 is going to be a combination of what you have learned over the past few weeks, right? Binomial heap / Fibonacci heap, disjoint sets, and so on and so on. Okay, so I will leave it to you to implement your own EP5. But once if EP5, this is what my heap is going to look like, right? It's a min heap, 0.1 G. Okay, let me show you how I've actually EP5 it. 0.4a, okay, 0.2b, 0.2c, 0.1e, 0.1e. Okay, so when you here I got 5 items, right? 5 double slash Q equals to Q means I will start from position number Q, which is here, right? Which is the node over here. Then I will perform a sync, right? Sync, I look at the left, right, which is I multiplied by Q. I look at the right, which is I multiplied by Q plus 1, right? 0.2, 0.1, 0.1. Obviously, I'm going to choose the smaller one, but since both is the same, doesn't matter what I choose. So I'm going to perform a swap. So here is going to be 0.1. 0.1 G, and here is going to be 0.2 B. Okay, then I begin from 2, then I minus 1, it will become 1. Note I'm using a normal min heap with array implementation, right? So I'm now here, right? And then I will perform a sync again. So I look at the 1 here and look at the 1 here, which is smaller. The 1 here is smaller, so I'm going to perform a swap, right? So I'm going to perform a swap. Here will be 0.1 G, and here will be 0.4A, 0.4A. I'm here in my sync. I look at the left, I look at the right is smaller. So here will be 0.1 E, and here will be 0.4 A. Okay, so after I perform EP5, what you see on the right will be my heap. Okay, what you see on the right will be my heap. Okay, so the frequency is not important anymore. I don't give a shit about it anymore, right? It's not important. Okay, so I'm going to replace it with encoding. So I'm going to build the encoding as I manipulate my heap. Okay, so what happened in the heap? I need to serve 2 times. Okay, so if you remember, how does your serve perform? Right, the root and the last element actually swap. So it will be 0. Okay, so you swap the root and the last element, then you remove the last element, right? So after I swap, it will be 0.4A, it will be 0.4 G, 0.1 G, then it will be disappearing. So the first item, right, serve number 1, give me 0.1 G. Okay, then I perform a sync, right? So I'm going to sync, I swap this 2, 0.4A, 0.1 E, then I continue my sync, 0.2 B, 0.4A, 0.4A. Okay, then I need to serve again, right? I need to perform another serve. So swap and swap, 0.4A, 0.1 E, erase it because I serve 0.1 E, then I perform a sync, right? So it will be 0.4A, 0.2 B. Okay, so I serve 2 times. When I serve 2 times, the first serve, right, serve number 1, which is only G, will receive 0, and my second serve E will receive 1. It's the same as me drawing G, E, 0, 1, G, E. Okay, then what's going to happen is I'm going to sum up both. 0.1 plus 0.1 will be 0.2. G and E will be GE. Then I will append back 0.2 GE. Then I perform a rise upwards. Okay, so the parent of 0.2 GE is 0.4. 0.2 is smaller, so I swap 0.2 GE, and it will be 0.4A. Then here I will compare with my parents. Parent of 0.2 GE is 0.2 B. Numbers are the same, but the alphabet, right? Remember, we want to prioritize the shorter tree. Shorter tree means I want lesser number of alphabet. B is only 1 alphabet, DE is 2 alphabet, so B is smaller, so I could not swap, right? So this is my if. Then I'm going to repeat the same process again, right? I'm going to serve. So the first serve will be 0.2 B, so it will be 0.4A, it disappears. Then I'm going to sync, so it will be 0.2 GE, and it will be 0.4A, right? Wrong. Okay, so here, right, when I want to sync, okay, I compare both 0.2 and 0.2, both is the same. GE, 2 alphabet, C, 1 alphabet. So when I sync, I'm supposed to swap with the item on the right, right? So in other words, your heap not only look at the number but also look at the length. So it will be 0.2c, right, and it will be 0.4a. Okay, then I'm going to serve again. What happens when I serve? Swap the last item with the root, so it will be 0.2c, 0.4a. It actually disappear, right? Then I sync, so it will be 0.2ge and it will be 0.4a. Okay, so what is the first alphabet, right? What is the first serve? The first serve is b, right? So b will receive 0. Second serve is c, c will receive 1, right? So what you're going to observe here is b, b, c, 0, 1, right? So then I'm going to submit 0.4 bc, put it back in 0.4 bc. Then I perform a rise, compare with my parent 0.2, 0.4. My number is bigger, so I'm good. Okay, then once again I'm going to serve, right? So the root 0.2ge, right? Swap with the last element and remove the last element. Again it's bc, right? Then I need to perform a sync, right? 0.4, 0.4, good alphabet, 1 alphabet. 1 alphabet should be the parent, 0.4a, 0.4 bc. Okay, then I serve again 0.4a, then I'm left with 0.4 bc. Okay, so now I'm going to do the same step. The first serve, I will append it with the first one will be 0, the second one will be 1. D and E, I will prepend 0. A, I will put a 1. So you notice it is a prepend. But what is the problem with prepending? Right, prepending means I need to shift. So when you were to implement it, unless you implement an implementation which allow you to prepend in O of 1, right, which is to use a linked list, or you can use an array you append at the end, and once you finish you flip it, right? Whichever implementation is fine with me. So what is going to happen here is you're going to notice the following, right? If this is the root, here I will have a. No, here 1 is going to be a. Then it will be 0, right? Then it will be D, it will be D, it will be E, right? So D will be 0, 0, E will be 0, 1, and A will be 1, right? So you realize as I'm manipulating my heap, right, I'm building the tree one by one. It's very different from what you see in your lecture slides, right? If you look at your lecture slides, it's more about like you build the tree, right? You put the king, only at the end you obtain of your encoding by traversing your tree. Okay, but what I'm showing you here is the shortcut, which is really, really fast, right? In fact, I don't even build a tree, right? You don't see me making a tree. The only thing which you see is over here. So what I'm showing you here, right, is no tree, right? It's very eco-friendly, no trees, right? And yeah, that's what it is. Then sum it up, it becomes 0.6 ADE, right? So put 0.6 ADE. Then I perform a rise, it doesn't change. Okay, then I'm now going to serve. The first serve will be 0.4 BC. Second serve is 0.6 ADE, right? And now my heap is empty. Just like the first one, BC, I'm going to prepend with 0. ADE, I'm going to prepend with 1, 1, 1. Okay, so because my heap is empty, I'm finished. Here will be the encoding for my Huffman. A will be 1, 1. B will be 0, 0. C will be 0, 1. D will be 1, 0, 0. E will be 1, 0, 1. Right? So if I were to build the tree, right, this is what you're going to see. A will be 1, 1. Right? A will be A. Okay. B will be 0, 0, 0, 0, B. C will be 0, 1, right? D will be 1 0 0 and E will be 1 0 1. You realize it is a prefix free tree, right? And I obtain the encoding without even building a tree. Right? I never even build a tree. Okay, so this is the shortcut which you should be using, you should be following for your assignment, right? And you notice I'm not using hash cable. Remember I say if you use dictionary or hash cable, you're going to be screwed, right? And here is actually very simple because A is ASCII of 97. I mean, it's the whole array of 0 to 255, right? Or 0 to 25, which you have done with your strives and your assignment 1. Okay, so with that, right, I finish Huffman encoding. From now on, every alphabet which you see is going to be encoded in the form of a Huffman, right? So this is your Huffman encoding. So if you were to look at the one here, right, if you were to look at the one here, this is how I can encode, this is how I can decode. So if I were to open your assignment tree, right, where is your okay, let us not discuss about your assignment, right? So if you were to look at your Lampersieve, right, if you see of this alphabet here, right, of your alphabets here, they will not be A big, A big, A big, A big, A big. They will be Huffman of A, Huffman of C, Huffman of B, Huffman of A, right? So here, if you were to look at my whiteboard, okay, A is 1 1, B is 0 0, right? So here will be 1 1, here will be 0 0, here will be 1 1, and my C will be 0 1, right? So they will not be 8-bit or an ASCII representation anymore, right? Awesome. Okay, so that's all for your first video. I hope you understand HuffmanCoding. I hope you can implement your HuffmanCoding moving forward, right? Make sure you use the shortcut I've described, right? I do not want to see you building a tree because building a tree is slow, it's a lot of effort, and why are you in computer science, right? Computer science is about being lazy, being efficient, right? So no tree, right? You need to use a heap. Remember, the heap needs to go through EP5, right? If you insert one by one, it's not EP5, it's not so efficient, right? Then it's just serve append, serve append, serve append, serve append. The first serve you prepend with a 0, the second serve you prepend with a 1, right? But the problem is your prepend actually have additional complexity, so you want to use either a link structure for you to prepend in O of 1, or you append, and then you flip it. Okay, so this is your first video which will be very useful for your assignment. Right. Good luck, have fun, bye.